Good afternoon. Welcome to the Trelleborg Sealing Solutions presentation on finite element analysis. My name is Eric Bucci. I'm the segment manager for Oil and Gas Americas with Trelleborg Sealing Solutions. And today I'll be discussing some properties of finite element analysis and how Trelleborg Sealing Solutions uses this powerful tool to help analyze seal and seal performance. To begin with, I want to explain a little bit about what finite element analysis is. For short, we call it FEA. FEA is a software program that can produce computer-generated models. And these models allow us to analyze a material or a product. And it's a tool that engineers use to graphically represent what happens to a seal or a material when subjected to stresses and strains. Specifically, Trelleborg uses Abacus and Mark software packages. Those are nonlinear FEA software packages for analyzing plastic and rubber materials. And we specifically use these programs to analyze seals. The software uses geometric shapes, such as a square or a triangle, and at each node or vertex of these geometric shapes, the computer connects these shapes to form what we call a mesh. And as an example here, I have a cross-section of an O-ring that shows geometric shapes all connected, forming that mesh. That mesh is then turned into either a 2D or a 3D model. A 2D model is usually a more simple graphical representation of an axisymmetric analysis, whereas a 3D model is a more comprehensive, complex model that gives you a circumferential view of the seal or product you're trying to analyze. So once this model is generated by the computer, we can subject that model to virtual forces and stresses. And the output can be shown as a picture or even an animation. And that synthesizes what would happen in the real world. And the output can also display the forces and stress magnitudes, allowing the engineers to see where the different stress concentrations are. So to give an example of this, here's a simple 2D analysis of a spring-energized seal, which for Trelleborg Sealing Solutions we call a VeriSeal, with the orange product being a backup ring. As you can see, we simulate the seal being installed. The top plate is coming down, compressing the seal into the groove, allowing it to seat. And in a second here, we'll subject the seal to temperature, which will cause the seal to expand. And after that, we will subject the seal to pressure. So the next step here is to apply temperature to the seal. And we'll give it 1 second to load. And as you can see, now the temperature is being applied to the seal. You can see the materials expanding. We'd use this to check for volume fill to make sure that when the seal is heated, it does not overfill or over-occupy the groove. Now pressure is being applied to the seal. As you can see, it's being moved to the left side of the groove. And for this, we check to make sure that there is no extrusion of the backup ring. In this case, you can see as the pressure is applied, it actually lifts the hardware up a little bit. Hardware does, quote-unquote, breathe as you apply pressure to it. So we have to make sure that the backup ring slides along the groove and does not extrude. And you can see at the bottom of the seal, there's a slight extrusion lip beginning to form. And that's to be expected because you cannot completely occupy the groove with the backup ring. This shows a very successful installation and function of the seal. Now for a more complex 3D analysis, here we have a valve seat represented as a blue. You can see as the valve comes down to close on top of the valve seat, the different colors forming represent the stress of the valve compressing the seal. And on the left side of the screen, you can see a key that shows the different magnitude of that stress. So as we compress the seal in the groove, this is a close-up shot, you can see how the seal begins to rock in the groove as the valve begins to close. The white line forming is the first stress concentration of where the valve seat hits the seal. And once again, we can determine the magnitude of that stress by checking the key at the left side of the screen. So as we close the valve further, which will load here in 1 second, you can see that the stresses begin to increase in the seal. We can also visually see how the seal reacts to the valve closing. In this case, you can see some of the seal is being pinched or extruded up the side, and that's an instance where is not an optimal application. So we would go back and redesign the seal to make it function properly in that application. So FEA can also be used for other applications. In this case, we can use it for side-by-side comparisons. In this graphic, we have two spring-energized U-cup shaped seals. The seal on the left has a corner reinforced backup ring. The seal on the right has a triangular shaped backup ring. And we can use the FEA to analyze how each design works when temperature and pressure is applied to the seal, and pick the best one before going into the real-world testing or field testing. The Trelleborg has other capabilities for FEA. In addition to the 2D and 3D analysis I've just described, we can also analyze materials such as elastomers, plastics, composite materials, and even the metals that comprise the hardware or the mating surfaces of the seal. We can do this statically, we can do it dynamically, we can do viscoelastic examinations, and also heat transfer. And the components for the sealing world we test are, of course, seals, gaskets, O-rings, even the metal springs inside the seals, and composite bearings. Continuing on with our capabilities, a VariSeal, as I mentioned before, is a spring-energized U-cup PTFE seal. And we can model the double-decker type designs of these VariSeals and also the large springs, and analyze the interactions of the spring with the jacket when temperature and pressure is applied. We can analyze the viscoelastic behavior of the seal, which allows us to predict friction. We can do it in a full 3D analysis and visualize how the heat transfer is affecting the seal. And finally, it's used as a tool for design verification and validation. Some developments that Trelleborg is working on currently are on the more complicated or intricate types of seals, such as composite seals. And these can be rubber seals with a fabric layer embedded in the middle, such as a diaphragm application, or in this case, a door seal. And we're also using model and process developments for our PTFE and elastomer materials, because the information that the FEA outputs is only as good as the information you input. So we make sure that we model our materials as thoroughly as possible, so the information going into the model provides the most real world type output. And this allows us to, once again, predict wear life and examine the viscoelastic properties. So the underlying theme here is Trelleborg has these capabilities. It allows us to analyze seals before they're used in a real-world application, which becomes very expensive. This tool allows us to do that in the computer, saving you money and time, and optimizing the design before it goes to the prototype phase. So please let Trelleborg Sealing Solutions know what we can do to help solve your problems in the sealing world. That concludes my presentation. Are there any questions? Thank you very much.